Hello, and welcome to the presentation on a project automated and rapid fault diagnosis of railway tracks using in-service train measurements. This is funded by Science Foundation Ireland with Dr. Abdullah Malik Jafrian as the principal investigator. I am Dr. Muhammad Arslan Khan, presenting our recent work with the fellow postdoc Dr. Amin Gyasi from School of Civil Engineering, University College Dublin. This presentation illustrates a recent study from our group relating the railway bridge monitoring technique. Here, a case study of the Malahide Viaduct is discussed. In 2009, two of its spans, span 4 and 5, and a pier collapsed due to scour caused by a flash flooding event. As a result of this collapse, millions of euros were invested to rehabilitate the viaduct in the form of two new spans and one new pier. They are also shown in the red box here. This could have been avoided with the help of effective monitoring strategy. Two main types of monitoring, which are direct and indirect monitoring, are compared in this study to assess the efficacy of the natural frequencies estimation from in-surface measurements. In the first phase, direct monitoring was carried out, which measured structure data using sensors directly attached to the structure. Here, the measurements were taken in 12 stages, each of different span using 5 accelerometers placed at mid-span, first, and third quarters and both ends of the supports. These sensors were moved from span to span in each consecutive stage, having one accelerometer in common to get the vibration data. This vibration data, caused by 3 passing trains, was measured from each span. These accelerations were divided into force and free vibrations, which were used to measure natural frequencies of each span. Here, a free vibration example is shown, with the figure in the right side indicating the significant peak, the first peak indicating the first natural frequency of the structure. The calculated frequencies from the forced when the train is moving on the bridge and free vibrations when the train leaves the bridge are shown in this table. Here, the green ones represent the results from the spans with 18.85 meters span length, and yellow ones inside the green box represent the frequencies of the new replaced spans, illustrating the higher natural frequency of the replaced spans as compared to the one with the equal lengths. This result from the direct measurements has also shown the effect of force frequencies being different and in some cases lower than the free vibration frequencies. In the second phase, data from the in-surface train was measured in the form of vertical bougie accelerations recorded over a 5-week period in 2016. In this case study, data from the train traversing over the viaduct 41 times was measured. The sensor was placed at the front bougie with the power supply coming from the train. A signal decomposition technique using ensemble empirical mode decomposition is applied to the accelerations to decompose a signal into multiple signals with different frequency ranges. These decomposed signals are used to estimate instantaneous frequencies in time frequency domain, calculated with the help of Hilbert transformation. Here is an example of the vertical bougie acceleration of the train when it traverses over the viaduct. The red box indicates the area when it traverses over the replaced spans, with showing that there is a decrease in the amplitude of the acceleration at that area. On the right side, there's the same signal showing in the frequency domain, showing that there are lots of frequencies and mode mixing for the train as well as bridge frequencies. These acceleration signals are decomposed using the signal decomposition system, and instantaneous frequencies are estimated. Here is an example of signal decomposition and instantaneous frequencies, where the acceleration signals from one train while traversing over the viaduct is decomposed into 8 signal and instantaneous frequencies. In this study, instantaneous frequencies closer to the range of spans natural frequencies are studied, and they are further analyzed. In this regard, the 6 decomposed signals shown here in distance frequency and frequency domains are used to estimate the natural frequencies of the spans. This is because of the frequency range of these signals lies closer to the natural frequencies of the span, which is in between 6 to 9 Hz. In the bottom figure, box area represents the time when 3 trains traverses over the new spans. In the phase 2, an average of the instantaneous frequencies from the 6th decomposed signal is calculated for each span to estimate the natural frequency of the. Here, the resulting frequencies are plotted in a form of error bars from the 41 runs of the train and compared with the phase 1 of direct measurements. Here showing the effectiveness of the indirect measurements from span for spans 3 to 10, which are having equal length, and an increase in the estimated frequencies for span 4 and 5, which are the replaced ones. The results for the end spans, which are shorter in length, are not as effective because of their higher frequencies, which may be covered with the help of different decomposed signal. This result shows that the indirect measurements from the in-service train measurements can be used to estimate the natural frequencies with a reasonable accuracy that can indicate the health condition of the bridge. Also in this study, average energies of the instantaneous frequencies from each span is calculated to show the structural change after the rehabilitation. Here at span 4 and 5, lower energies indicate the replaced span being stiffer than the existing ones. This parameter can also be used to assess and facilitate bridge monitoring using in-surface train measurements. In the end, I wish to thank Science Foundation Ireland for funding the research and University College Dublin for providing the appropriate facilities. Thank you.